Vamos con esta, ¿no? Welcome everyone. Today, the doctoral program in water resources of the Faculty of Engineering and Department of the Water Resources and Environmental Science of the University of Cuenca are glad to present this thesis project defense. We're glad to introduce the doctoral candidate, Engineer Mario Córdova Mora, who will defend his thesis project entitled Precipitation Drivers in the Tropical Andes, Teleconnection, Dynamics and Implications for Precipitation Forecasting. Now we introduce the committee, who is led by Professor Dr. Rolando Seyri as supervisor and Master Joana Oriana as advisor. And the jury constituted by Professor Dr. Cindy Chelito from the University of Northern Colorado and Professor Dr. Esteban Samaniego from the University of Cuenca. The head of the doctoral program, Dr. Luis Timby, is also give his welcome to everyone, and we are going to give some instruction from this session. The candidate will have approximately 25 minutes to present his project. Then the jury and the committee will deliver, the jury will deliver some questions and start the discussion with the candidate. And the public will also deliver some questions, and they will have the opportunity to participate with some discussion. So then we kindly ask to the public and other participants to turn off their audio and video to give the opportunity to the candidate to present in a proper way his presentation. And well, we kindly ask to Mario to start this presentation now.
Thank you, Galo, for the introduction. I'm gonna share my screen now, and I would just like the confirmation that you're seeing it.
Sí, está bien.
No. Do you see it in full screen now?
Yes.
Sí.
Yes, perfect.
Okay. Bueno, antes de empezar, quiero solo tomarme un par de segundos para decirles buenos días a toda la gente que está conectada. Es un gusto ver a tantos amigos, a mi familia. Y gracias y bienvenidos a mi presentación. So, good morning, everyone. Thank you for attending my presentation. Special thanks to the members of the jury who agreed to read my proposal. And yeah, I'm looking forward to the discussion we're going to have by the end of my presentation. So as Galo already mentioned, the title of my thesis, you can see it now. So the main goal of my PhD project in the end will be to implement a precipitation forecasting model for the tropical Andes. But first, in order to achieve this main goal, this final task that I want to do in my PhD, I will study the teleconnections, the dynamics, and the climate in the tropical Andes and how it is connected to precipitation in the region. So first, I would like to start with stating the importance of the tropical Andes. As you may know, millions and millions of people depend on water that is originated in this mountain range. Just as an example, here in the picture on the right, on your screens, you can see a picture of the city of La Paz in Bolivia, which is only an example of one of the many large cities that depend and rely on water that is originated from this mountain chain. But we don't only rely on water from here for our consumption, but also our economics depend on this. Just here to set another example, here we see a picture of a hydropower plant, which is one of the main sources of electricity for the region. So what is the connection between water availability and climate? Well, of course, water availability mainly depends on the rainfall amount that falls in the region, and this is directly connected to climate. So I would like to give you first a brief overview of the climate of the region and some of its characteristics, and especially the ones that are going to be important for my project. So first, in this slide, I would like to talk to you about the two main gradients of climate that we have in the tropical Andes. That is the portion limited to the northernmost part of the South American continent, so around 12.5 degrees north, as you can see here, and the southern limit is defined as 25 degrees south. So first, I want to talk about the zonal gradient that we have in the tropical Andes. So mainly, as we can see in this figure on the left, that shows the annual cycle of precipitation for the continent. In general, we can see that north of the equatorial line. We observe the annual cycle of precipitation with the highest amounts of rainfall falling in the months of June, July, and August mainly. And we can see that the opposite occurs in the southern part of the continent, just so south of the equatorial line, with the highest amounts of precipitation falling during the months of December, January, and February. But we also have a mixed signal around the equator, where we have two peaks of precipitation during the year, and this is because of the double passage of the ITZ throughout the year in the deep tropics. But we also have a meridional gradient that can easily be observed in the satellite image that is shown in the right, where we see that the Andes act as a natural wall to the moisture that is brought by the trade winds that carry humidity from the Atlantic, from the tropical Atlantic, and also from the Amazon basin. But they encounter this natural wall that are the Andes, and we can see that to the western side of the Cordillera, there are these more arid and desert areas, and to the eastern side, we observe that wetter conditions prevail, and we have these greener areas and more vegetation. So this already is a signal that the complexity that we can find in the region, and this is already a clue that we cannot study the tropical Andes as a whole, so we have to come up with better ways to do it and to study the region. So a little bit more about the climate of the Andes, of the tropical Andes. Here in this picture on the left, I just want to highlight that the South American continent is surrounded by the Pacific Ocean, the Atlantic Ocean, and the Caribbean Sea. And the sea surface temperature of these water bodies, of course, influences climate in the region, and then in the end, precipitation. Here in the picture on the right, we can see some of the climate processes and atmospheric processes that affect the climate of the region. Mainly, we can see these two black thick lines that highlight the position of the ITZ in September, in this case, the upper one, and the lower one, the position of the ITZ in March. So this is what mainly drives this zonal gradient of precipitation that I showed you in the previous slide. But we also have some more patterns of climate circulation. For example, we have the South American low-level jets, which brings moisture and distributes it along the continent. We also have a couple more of jets that are not portrayed in this figure, but that are responsible for these high amounts of rainfall that are observed in the Pacific coast of Colombia and northern Ecuador. And we also have some other climate circulation patterns that occur in longer timescales. I'm talking about decadal or interdecadal timescales, such as the Atlantic meridional overturning circulation that is shown in this arrow here. And we also have some decadal circulation patterns in the Pacific, such as the Pacific decadal oscillation. So now we have more clues about the timescales that play a role in the climate of the region. And we also can know now that it's not possible to study only using one timescale, so we have to put more focus on that and divide it, also our data in different timescales to be able to understand and unravel the relations between climate and precipitation. So, as I already told you before, precipitation is directly connected to water availability. And why is it important to in the end make a good precipitation forecasting model? It's because, well, as we know, climate is changing and it will keep changing in the future. Here I'm just showing a figure of one of the many climate predictions that well, this figure specifically, it shows how precipitation will change by the end of the 21st century. And when we zoom into our study region, we also see that complexity emerges. We see areas where precipitation will increase, and we also see areas where precipitation will decrease. So why is it important to understand the connections between climate and precipitation? Well, I would like to argue that it's because precipitation is one of the most difficult variables to forecast and to predict. And then it will be useful to understand how other variables that are more easily predicted are connected to precipitation. And this will help us in the end to have a better precipitation model based on more easily precipitation variables. So this has not been done in the past. A forecasting model for the tropical Andes does not exist yet, at least not one that considers all the variables and all the times and special case that I will be considering in my PhD project. So the general objective of my PhD research will be, as I told you already, to implement a precipitation forecasting model in the tropical Andes, and I will be putting a special focus on southern Ecuador and northern Peru, and I will tell you a little more about this later. And this will be accomplished through gaining new insights on the teleconnections and dynamics that drive precipitation in the region. So before I start with the specific objectives of my project, I just want to show you this slide with a flow chart that shows the structure of the PhD project. Right now, I'm not gonna go into the details of every one of the blocks you see here, but I just want you to take the big picture from here. My PhD is gonna have 3 papers as an outcome. Each one of the colors corresponds to each one of the papers that will result in the end. And it will be divided in 5 working packages. Each one of the columns corresponds to each one of the working packages. So as you can see, the first paper and the second paper, they are both divided in 2 working packages, and the last one is only 1 working package. So the main thing here is that the color code, as it shows, yellow plus blue, it makes green. So all the knowledge that is gained in the first 2 papers and in the first 4 working packages will be exploited in order to implement the precipitation forecasting model for the third paper. So now I'm going to be telling you a little more in detail about the first paper, which will deal with identifying the precipitation drivers in the tropical Andes. So zooming into the part of the flow chart that concerns us now, we can see, as I told you already, that I will have 2 working packages for the first paper. The first one will be about regionalizing precipitation in the tropical Andes. So as I told you before, they cannot be studied as a whole. So I will be dividing the study area into different regions that have the same climate. And so precipitation can be studied together and the drivers can be determined for each one of the clusters. So once I make this regionalization of precipitation, I will go to the second working package, which is about finding the drivers that control precipitation in each one of the regions. So this is the study area, the tropical Andes, and as I mentioned before, they are limited to the northernmost part of the continent, of the South American continent, to 25 degrees south. And I chose to limit the Andes as the areas above 300 meters above sea level, and this is what we see in this figure here. So what is the data for the first working package, which is about clustering and finding coherent regions of precipitation in the tropical Andes? I will use the GPCC monthly dataset, which is a global precipitation dataset over land. And here we can see a figure of this dataset. It shows precipitation for the month of July this year. And to extract the areas above 300 meters that I decided to define as the Andes, I will use the SRTM digital elevation model. So how will I do the regionalization of precipitation? I will use the K-means clustering technique. And as an input for this technique, I will use the annual cycle of precipitation in every pixel of my dataset. But besides that, I will also use the latitude and longitude of the pixels to make sure that the clusters have spatial cohesion. And I will use additionally the elbow method to determine the optimum K, which is the number of clusters in which the study area will be divided. Then I will go to the second working package, which will be about finding the different drivers for the different clusters. And of course, the data, the most important part, is going to be the clusters that I will find in the first working package. And I will try the different climate indices. In the left, you can see the climate indices, the traditional ones, as I will refer to them in this presentation, are the ones from NOAA. Some of them related to ENSO, some of them related to the tropical Atlantic sea surface temperature and the Caribbean sea surface temperature. other couple indices related to these circulations in the Atlantic and the Pacific Oceans that happens in longer timescales that I mentioned in the introduction, and some other complementary indices that are related to ENSO. I will additionally use the ERA 20 series analysis, and I will use these variables to try to find among them also the possible drivers of precipitation. So I will use variables that are related to winds, variables that are related to moisture in the atmosphere, variables related to convection, and also variables related to the vertical velocity of winds. So how will I proceed to determine the drivers of precipitation for each one of the regions? First, so as you know, the reanalysis dataset is a spatial dataset, and this is not it cannot be used together directly with the indices from NOAA, for example, because they are only time series. So first, I will build empirical indices based on this dataset. I will perform a seasonal analysis. So I will be studying the seasons of December, January, February, and June, July, August separately. And I will use a random forest regression to determine the drivers for each one of the regions and each one of the seasons. I have already been working on this some time now, and I have some very promising results, I think, but I will show you this later in the presentation. But now, for now, let's just stay focused in the PhD project itself. So now I'm going to tell you a little bit about my second paper, which will be about identifying the drivers, but in the equatorial Andes. So now, again, zooming in into the part of the flowchart that corresponds to the second paper, it's again divided in two working packages as before. The first one will also be about some pre-processing of data, as in the first one I did to find different regions of precipitation. In this one, instead of finding different regions of precipitation, I will do a weather typing analysis to find similar storms or similar events. And then in the forward working package, I will try to identify the different drivers for these different weather types of rainfall events that I will find in the third working package. So this is my study area for the second paper. So you can see here, it is located in the southern part of Ecuador and in the northern part of Peru. And you can see in the white circles is the area coverage of the 4 weather radars that are installed by the RadarNet Plus project. And so I will have the events from these weather radars as my data for this second paper. So as I told you, the data for the third working package will be the precipitation from the weather radars of the RadarNet Plus project, which is run by these institutions. And this is a picture of the CAX radar, which is the northernmost radar of the project, and it's located just a few kilometers from the city of Cuenca. So what is the method that I'm going to use for the third working package, which is about doing a weather typing analysis of these rainfall events that will be measured by the radars? I will use the self-organizing maps algorithm, and here in the right, I'm just showing an example of a weather typing analysis that was done by Muñoz et al. in a study of them a few years ago. So I just want to give you an idea of what my second paper will look like. So here we can see the weather typing they performed, but using geopotential height anomalies. And I will use precipitation instead, because I want to find different clusters of storms that have the same characteristics, and potentially they will be explained by the same climate circulation patterns and the same climate states of the climate. So you can see here that spatial patterns emerge. They are very distinct, and they use daily data. And here you can see that each one of the days that they analyze falls into one weather type. So what I will find is I will have rainfall events as input, and each one of my rainfall events will fall into a weather type that I will study separately. So the data for the fourth working package, which will be about determining the drivers of those events, will be, of course, the weather types. and I will use the ERA5 reanalysis that has a 1 hour resolution in time and 0.1 degrees resolution in space. How will I study the drivers? How will I determine that? I will use composite analysis, which is a very powerful and very common technique used in the atmospheric sciences. Again, I want to go back to the paper by Muñoz, and here these two figures show composites they made for two different variables, but that they correspond to the weather types that they found for the geopotential height anomalies. So in the left, we see the composites that correspond to precipitation anomalies, and on the right, we see the composites that correspond to sea surface temperatures anomalies. So what we can see here is that also very clear spatial patterns emerge in these pictures, in these composites, and they allow to make hypotheses about the states of the climate that are related to the different weather types, how they produce precipitation anomalies, how is the sea surface temperature anomalies that are connected to each one of these weather types. So what I plan to do is to build composites of different variables that will potentially explain the different weather types that I will find for the different events. And this will allow me to understand the state of the climate that drives these different storm types that I will find for my second paper. So all of that knowledge will bring me to the third paper, which is about the precipitation forecasting model itself that I want to do as the final goal of my PhD project. So again, just to highlight the fact that all of the works done in the first, all of the work performed in the first two papers will fit the model or the third paper. So the data for the fifth working package and the third paper is everything that I used before for the first two papers, but mainly the input is the knowledge. So the main input is going to be the drivers at seasonal scale that I will find in the first paper, and the drivers at event scale that I will find in the second paper. So at this point, as the members of the jury, you read my proposal. We didn't want to be very specific about how the precipitation forecasting model will be. We didn't want to limit ourselves by stating right now what's going to be the spatial scale, what's going to be the temporal scale, because we're going to have a broad range of possibilities coming from these first two papers. So we're going to have drivers at different scales in time and space, and we're going to have also different lead times in which we can use for the forecasting model. So we want to keep our options open in that sense, but what we know already is that we will test machine learning techniques for the model that is going to be the third paper. So the plan for now is to use random forest, as it is a simple algorithm. It's an ensemble type model, and it's also useful for variables that have complex and nonlinear relations, as are the ones that we are dealing with in this PhD project. But we also plan to use deep learning, as this has been an algorithm that has been used recently in the environmental sciences, and it has been showing very good results in the past. So now I want to go back a little bit to the first paper and show you the preliminary results I have already. So first, I want to show the results of the clustering, so the results of the first working package. As you can see on the figure on the right, I decided to use K equals 10, so to divide the study area in 10 regions. And here we can recognize already some areas that are known from the literature. So for example, the cluster number 2, that is the darker blue one, it shows the Atacama Desert. Cluster number 7, which is the lighter orange one, it shows the rainfall hotspots in Peru and Bolivia. And the cluster 6, that is the red one, it shows the Chocó region, that is arguably one of the wettest regions in the world. So once this was performed, the analysis comes to identify the drivers for each one of these regions. The thing that I want to emphasize is about how I built these empirical indices based on the reanalysis data I was telling you about. So for this, I apply the same reasoning that is used for building, for example, the ENSO indices, in which they they find the areas of the Pacific Ocean in which there is higher correlation of sea surface temperature anomalies with precipitation anomalies in the coast of Ecuador. So by applying this same reasoning, I calculated the correlations between precipitation anomalies for each one of the different clusters and anomalies of the different variables from the ERA 20 series analysis. So here we just see a couple of examples in these two figures. In the figure on the top, we see the correlations between precipitation anomalies and the total column of water vapor for December, January, February for cluster 10. And we see the same, but for June, July, August in the figure in the bottom. So what I chose to do is to take every pixel in these maps that has a R² higher than 0.4 and a p-value lower than 0.1, and to average those areas to create the empirical indices. And I have an index for each one of these 6 variables that are listed here. And I also took the positive and the negative areas of correlation separately. So potentially we have 2 indices for each one of the variables, for each cluster, and for each season based on this ERA 20 series analysis data. Once I did that, I ran the random forest regression and using as input the empirical indices I just showed you, and also the NOAA indices. And here in this table, you can see the correlation coefficient values for each one of the clusters and for each one of the seasons. And in bold, I highlighted the correlation values that are higher than 0.5. So for December, January, February, you can see that 9 out of 10 clusters have a correlation coefficient higher than 0.5. And for June, July, August, 8 out of 10 have a correlation coefficient higher than 0.5. So I think this is already very promising. Of course, there's still room for improvement. There are some extra things that I want to try, but I think this is going in a very good direction. But in the end, what is the objective of my first paper? Is to find and determine the main drivers of precipitation for each one of the regions. And right now I have many indices that are going as an input for the random forest regression. And of course, they are not gonna all explain precipitation in every one of the regions. So I'm gonna take advantage of the algorithm, of the random forest algorithm, and one of its attributes is the importance of the variables that go as an input for the regression. So just as an example here, I want to show you these are the importances for cluster 1, for December, January, February on the left, and for June, July, and August on the right. And we can see here that, for example, the positive side of Cape is the most important one for the picture on the left. And we can see that even if when we're studying the same cluster, not the same variables are the most important ones to explain precipitation. So now the next challenge and the biggest challenge, I think, for the first paper will be to be able to physically explain these results and why the variables that we are seeing here that are the most important ones for the different clusters, why they are the most important ones, and what does this mean physically. So this will help us in the end to understand the climate better and build a better model in the last paper. So just once again, I would like to show you my schedule that you saw already in my proposal. So as you can see, the execution of the project is feasible in the 8 semesters or 4 years of the PhD. The first paper is planned to, in the schedule, is planned to be finished by April next year. And I think that will be very likely to happen. So I'm looking forward for what comes next. And I'm confident that I'm going to be able to finish my project on time. I just want to thank the Dirección de Investigación de la Universidad de Cuenca and to DFG, that are the funders of the project that has hired me for my PhD studies. And that would be all for me. Thanks for your attention, and I'm open to questions now.
Well, we are grateful for your presentation, Mario. Now it is time for the members of the jury to start with their questions. Professor Cielito, please begin.
I'll be just a moment here. I'm getting my notes together.
Yeah.
Hi.
Hello,
Can you hear
Sylvia.
me? Hi.
Yeah, perfectly.
I want to start by thanking you for a very clear presentation and a clear proposal. And I'm really excited by your initial results here. I'm excited to see that you're trying to do something that nobody's done before, to try to make these connections between rainfall and all of these different indices. I think I want to start, I guess there are a few clarifications that I'm going to ask you about first. Now, some of this is new to me because I'm not an expert on deep learning, and some of the AI that you're doing is, and that's part of what makes this really exciting, is this is really cutting edge. So I'm really curious about how you will identify some of the physical processes, or how you will think about some of the physical processes here. And in particular, I'm wondering, especially in mountain regions, there are local influences on precipitation that can have a very big impact. And how will you think about pulling or teasing that out of your results, or how will you think about, I mean, is it possible even to separate that effect, do you think?
You mean the local effects because of the mountain? Yeah, that's what I think it will be possible to do thanks to the weather radar observations that we have now, because though the resolution of those observations is unprecedented for the Andes. We have an image every 5 minutes, and we have very small pixels. So I think that will help a lot with the understanding of the precipitation locally in this area where the radars are. And now I'm just excited to see how good the ERA 5 reanalysis will work, and how I hope it works well, because I think it's the highest reanalysis resolution so far. And I'm just looking forward to start exploring that, because I haven't done it yet, and I think there's a great potential there to be able to connect the climate to these observations that we're going to have with the radar. So I'm touching the part of the AI techniques that I'm going to be using. So the thing is, the proposal is that I want to use the AI to produce the models, to make the regressions, to find what are the better predictors. But then in the end, what I think is novel of this project is that I will try to combine the expert knowledge of someone that knows about climate processes, and to be able to make these models not a black box anymore, or not much of a black box anymore. So try to come up with a physical interpretation of the results that these AI models will give us.
Great. I noticed that you're using the ERA 20 for your current work, the work that you did this year. Is that because the ERA 5 is not fully available yet, or is it?
It's because the ERA 5 goes only back to 1979, and I would like to have a data set as long as I can get, mainly because of these decadal oscillations. And we haven't talked about my work in a long time now, but I already, in my master thesis, I already used the GPCC data set together with the ERA 20C reanalysis, and I had some nice results. I think that it's a good data set that goes back as long as I can expect, and that's why I am using it, because it's just the longest one.
Okay, that answers another of my questions too, because I was going to ask about the GCPP data set, and how well that aligns with the ERA 20, because you're identifying these regions with the GPCC, and then you're using the indices from the ERA 20. So I wanted to make sure the precipitate, but it seems like it captures the ERA 20 captures the precipitation fairly well.
Yeah, well, I'm not using precipitation itself from the era.
Okay.
I'm just using it for the other variables. And
you're using for the geopotential heights and all the other water vapor. Okay, got it. Great. Another thing I wondered, so you're looking at data that goes back, I mean, in the era 20, maybe, was it, they go back to the 100 years or so?
Yeah, they go back to 1900.
Okay.
Yeah.
I'm also wondering if you are going to find a way to take into account climate change over the 20th century. I mean, how does this affect your study, and especially changes in the Amazon over the last 50 years may have impacts on water vapor, evapotranspiration, precipitation.
Yeah, right? that is actually something that is in our to-do list.
Okay.
In one of the last meetings I had with Rolando and Joanna, that are my supervising team, we talked about seeing how maybe doing an analysis decade by decade and seeing how climate change in the late 20th century affects the results, because maybe it could happen that the relations have changed, that the variables that control precipitation now are not the same that were controlling precipitation before. So yeah, that's definitely on our minds, and I guess it's one of the next steps we're gonna take in the research for the first paper. Yeah, but that's good. That's great advice. Yeah.
Okay. My other question was about, so in your first paper, it looks like you are doing a seasonal analysis to build your indices, correct? I'm wondering, because there are some phenomena that are occurring on a sub-seasonal scale. I'm thinking like the MJO, which you know, will the seasonal analysis miss some of these shorter these phenomena that occur on a shorter time scale?
Yeah, for sure, because to start with, the data is monthly already. So I'm already missing a lot of these shorter scale processes. But yeah, I think maybe this will be complemented by the work of the second paper, where I will be studying individual events and storm events. So I hope I can have a clearer picture by the time I finish the second paper. So like mixing together these seasonal results that I'm working on now, and then mixing them together with the event scale analysis, then I will be able to study MJO, for example, and maybe breeze systems in the mountains, or some other processes that occur at shorter time scales. So yeah, the shorter time scales I'm postponing them.
Okay,
for the
so that's
paper.
another paper.
Yeah.
Well, I was also thinking about the low-level jet, which may be seasonal related, but probably occurs on a time scale that's doesn't have the same regularity. So that may also be hard to identify the influence of that.
They also work in events, right? Like some days where the jet is just stronger, even though it's the jet season, but yeah, they are also isolated events. Well, I hope I can, as I am studying anomalies, so I'm working with precipitation anomalies and climate anomalies. I hope that at least I am taking into account years where the jet was more active than others, or less active than others. And I think the variables that I'm using both wind speed directions. I think those are good indicators for the jet activity. And yeah, I think that could be showing some of these phenomena, of this variability of the jet activity.
Okay. Well, I think those were my biggest questions. I may end up coming up with more after I hear you, but I'll turn it over to my other jury members here to ask you questions. Sure.
Yeah. Thanks.
Okay, thank you so much, Cindy, for your intervention here and your questions. So now we will continue with the question from Professor Samaniego, please.
Thank you very much, Galo, and thank you very much, Mario, for your presentation. It was a very clear presentation, and also you are dealing with a very exciting topic, and you're gonna use very cool methods. So I think I think it is a very promising PhD proposal, and I think that also this idea of combining expert knowledge and machine learning, as you said, is I think is the way to go, especially in our department, because in our department we have been very pluralistic about methodologies, and we have used both processes-based approaches and data-based approaches. And I think trying to get the best of each one is the way to go. And also, I also agree with your idea about trying to use information about variables that are somehow easier to predict. I mean, easier than precipitation, because as you said, precipitation is not very easy to predict. I mean, especially for global climate models, precipitation is temperature somehow global climate models. You get predictions that are very likable. That are very trustable. You can trust on those predictions. But precipitation is always difficult, and also in our region, as you know, we have a lot of convective activity here, and global climate models have very strong difficulties. It's very difficult for them to predict precipitation accurately. So I think what you're trying to do is a very interesting path, a very interesting research path, and I also congratulate you and thank you for. And I say thank you because you know that it's something that about which I'm very interested. I'm very interested in this topic, so I'm very anxious to see the results you're going to get. I also think that your presentation is very your proposal, the written proposal is very clear also, and very well structured, very easy to read, and the presentation has been a very nice complement to the document, to the written document. And so I think that you have done a very nice job. So I know that's also the work of, I mean, it's mainly your work, of course, but also the work of your supervision team. About the proposal, I also have questions. I mean, I think that the general idea is very clear. I only have some questions about certain specific issues.
Yep.
The first of them is I was wondering about the teleconnections, and you also you kind of answered something about that before. But I wanted to ask you about about your opinion regarding teleconnections as a way to build models to predict precipitation, because considering that climate is changing, you can think about, as you said previously, Professor Shalito also asked you, of course, climate is going to change and teleconnections could change. So you are kind of trusting that somehow teleconnections are going to be stable in some sense, or I mean, are going to be continuous in some sense in the future. But actually, there are some results that show you know very well about causal analysis. We have been working on that with you, and there are some there is some study that shows that connections may probably get every time they're going to be less strong. You know what I mean? They're going to. I mean, the connections are going to somehow fade away with climate change. Yeah. So we will have a less connected climate system, let's say. Yeah. So there are results in that direction. So my question is, what do you think about that? Because you said something, but I think that's very important. Given the approach you are taking. Yeah. What do you think about that?
Yeah, I think that there are two aspects I would like to talk about regarding this topic. Well, the first one is what we already discussed a little bit with Cindy, that it would be nice to see how these connections change already in the study period that I'm considering, which has been the period with the more dramatic changes we have observed in history. So I think that will already give us some clues on what we can expect in the future if we see that these connections are changing a lot in our study period, and that what was happening in the 1960s is not the same that is happening now. This can already give us some clues that, yeah, we have to keep that in mind if we cannot build a model today and say that this model will work 50 years from now. But I think at the same time that with the methodology that I'm working with, there's great opportunity to always improve your model, right? Because these indices that I'm building based on the ERA 20 series analysis, they are just a methodology. It's just finding correlations between precipitation anomalies and climate anomalies in the whole continent. So we can do that. We can keep updating our indices. We can go back every 10 years or so. I don't know how frequently we will have to do that, but we have a methodology that will allow us to update our climate indices, to realize that these things are not working anymore. They are not the same as before. Maybe we cannot even calculate indices anymore because correlations are going to disappear, for example. So I think it's nice to have this historical data already that will give us some clues about what to keep in mind for the future. But it's also nice to have a methodology that I think it's quite simple and can be easily updated and repeated in the future to see if things are changing.
Okay, yeah, that sounds very reasonable. I also wanted to ask you about another thing you already talked about, yeah. And that's the issue of the global against local, let's say, yeah. Or actually how global and local combine to get good predictions for rainfall, for precipitation. And I was thinking that this has, let's say, two aspects. and this question is going to have, let's say, two aspects. The first aspect is about the indexes you're using, these empirical indices.
Yeah.
I have the impression that they somehow, maybe you cannot talk about local information, but somehow you're getting some mixture between global and regional information.
Yeah.
Do you think that, I'm going to ask you this first part, and then I will continue, but I want to hear your answer about this. So what do you think about these empirical indices? Do they have some kind of combination of global, regional, and local information? What do you think about that?
I would say that they have more of a global and regional information within them. I would say that not a lot of local information is contained in those indices, and mainly because of not only because of the spatial scale I'm using, but also because of the time scale, because I'm analyzing seasons. And yeah, these local effects they happen more in also shorter time scales. So I think these indices are containing more of global and regional effects of the climate. So for example, I would say that they are going to be related to ENSO, for example. We will be observing that on the wind, for example, at the different atmospheric levels. That's also affected by ENSO. But as we were talking with Cindy a few minutes ago, we will also have more regional aspects like these anomalies in the jets, in the atmospheric jets, for example, that are going to also be reflected in moisture and in wind speed. So I think these indices for now, for the first paper, are global, a mixture of global and regional aspects of climate, I think. Yeah. Okay.
So then the problem of introducing local information is there still to be studied. And what I was thinking is, I like the approach you are taking, because as you said, you're kind of trying to build a methodology which can be updated in case of you notice some kind of a huge change in climate. Let's hope it is not so huge, let's say. And that's connected with the elections.
With elections next week.
Before the presentation, but in case there are changes that require some updating of the modeling of the model, that the methodology is very, is very flexible, and I agree with you. That's a very important advantage. But I have I was thinking that regarding the inclusion of local information, somehow that's because some research that I have been doing, especially with you know this research with Daniel Mendoza,
yep.
and he actually is kind of his idea is somehow to use let's say a coherent framework based on stochastic processes, and then somehow what we have thought is that maybe somehow you can introduce global information by means of teleconnections that you can introduce in the model, especially to drive as drivers of the harmonic components of the signal, or well, not really harmonic, but pseudo harmonic or quasi harmonic components of the signal. but of course, then you have to assume that somehow you can do an additive decomposition of the global part to make the difference with respect to the local part.
Yeah.
So you kind of have two terms in an additive decomposition, global and local, somehow. But of course, that you can do easily, or well, maybe not easily, but it's easier to think about this if you have like let's say, a coherent framework.
Yeah.
But your methodology somehow is more, let's say, flexible, which has some advantages, as you say. Yeah. I agree with you.
And
but
what
do you think about these two aspects of the methodology? How would you weight the pros and cons of your methodology against this, let's call it only one, a methodology based on only one theoretical framework? What would you, what do you think about that?
Yeah, I think, now that I think about it, I haven't really thought about it before, is that I'm gonna have very different results from my first and second paper, right? In my first paper, I'm analyzing time series of data, so I can study these kind of things, that how the global climate and the global teleconnections and circulations are connected to rainfall. But then I will not be able to do that kind of analysis in the second one, because I will not be studying time series, I will be studying events. So I'm just going to be connecting like snapshots in time, right? Take a snapshot of the climate and how this is related to precipitation and what kind of event it produces. So yeah, I think that's going to be the great challenge of the third paper, when once I start to think about building the forecasting model, how to merge this information from the two frameworks that I will be using. So yeah, I don't know yet, but it's great to start to think about it right now. Yeah.
Okay. My last question is about the composite. How do you call it? The composite
analysis. Yeah.
The composite analysis. Could you elaborate a little bit, because I don't understand very well. Do you kind of make some kind of weighted average or linear combination of the different variables? How do you do it, more or less?
Yeah. So I will show you the figures again. So for example, in this paper, they did the weather typing for geopotential height anomalies, right?
Yeah.
So they used daily data, and they classified each one of those days into a weather type. So what we are seeing here in this figure is the average of the 327 days in this case that belong to the weather type number 1. So they have, I will do this with the rainfall events, right? So I will have different clusters or events that are similar, so that have similar characteristics. But the nice thing about having this type of clustering is that then you are able to, because you know what day falls into every one of the weather types. And then you can take, for example, as they did here, the precipitation anomalies for each one of these days, and also average that and how this looks like. So what is the precipitation anomaly related to this geopotential height anomaly? It looks like this. And what is the sea surface temperature anomaly related to these geopotential height anomalies and these precipitation anomalies? It looks like this. So it's very simple, actually. It's just taking the days that corresponds to each one of the weather types and averaging them, and studying the spatial patterns that emerge, and trying to find the physical explanation of why is this sea surface temperature anomaly related to this precipitation anomaly and to this pressure anomaly, which is portrayed by the geopotential height. So I plan to do that with events. I will have, I don't know, depending on the duration of the events, but I will have these 2 hours. They correspond to this weather type 1, and then I will be able to analyze in those 2 hours maybe, or maybe in the days before, how the sea surface temperature was looking, how the wind was looking. So I will be able to find these spatial patterns or these states of climate that are related to each one of my storm types. I don't know if that's a bit clearer now.
Anyway, we can talk about more details sometime, but I think it's clear now. And well, I can see Galo is going to stop me now. So thank you very much, and
thank you, Esteban.
I congratulate you. Congratulations, because it was a very nice presentation.
Thanks for your questions and your comments.
Okay, thank you so much for the members of the jury for their appropriate questions. Now we have time only for 2 short questions from the public. Please provide your question in English and use the button raise hand in the participants tab of your Zoom display. We will allow only 2 questions, a short question, please, from the public. Okay, please, Daniel. And Luis Pineda, please. Daniel, you can continue with your question.
Okay, can you hear me?
Yeah.
Okay. Congratulations, Mario. It's very interesting. You have to do a lot of work, I think. But it's very nice. It is very nice. It's a very interesting topic that you have there. And sorry for my English first. I apologize for me. My English is not the best, but I will try to make myself understand. And the first thing is that, as you know, I have been working with this topic for 4 years, and I already established some connections with the global and local connections, and I built some quite a model I'm trying to testing right now. It seems to be well, at least for a monthly scale, right?
Yeah.
But when I was doing my first paper about the teleconnections, the thing was that one of the questions of the reviewer was that, okay, you have a methodology there and you are using some features in your data, but it seems that the teleconnections are sensible to the length of the data in the first place, and also it seems that they are very sensible to the methodology. So it depends on the features you are using there, right?
Yeah.
And that was my first question. I replied the questions because it was very interesting for me. It was a very interesting experience to try to understand that. It was to try to understand what happened with the teleconnections there, and what happened with the things we are using right now. For example, the features and dynamic harmonics regressions, or some people use wavelets to establish that connection. So the specific question is, what makes the framework, the whole framework you are using there, think you that you are doing something special in teleconnections?
Yeah. So, well, first, as you mentioned, of course, the longest your data sets, the strongest the statistical significance your teleconnections are going to have, right? Because there are some processes in the climate that happens, like ENSO, for example, it happens every 4 to 7 years. So if you have, for example, only 20 years of data, you're going to have 2 or 3 events, and that's not strong enough to determine the teleconnection. So I think one of the main strengths of my study is that I'm using a very long data set. I'm going as far back in time as I can go to try to get out the most information out of the data that I can get. And I also think so that's on the side of the time scale I'm using, or the time period I'm using. And on the other side, I think another strength is that, as you said, it's also going to depend on the method you use to determine your teleconnections. But well, in the end, what teleconnections are simply correlations between one climate variable and another, right? So I think I'm using as the same technique they use to establish the Niño indices, which are indices that indicate teleconnections between sea surface temperature and precipitation anomalies in some regions. So I'm using this very, very simple technique, which is only, again, correlating precipitation anomalies to climate anomalies of other variables and find spatial patterns and where these variables are going to affect more precipitation. So I think the combination of this very long data set and this very simple approach I'm using to establish my indices, which are my teleconnections, I think that's what makes my study strong. Yeah.
Okay, that was very interesting. Can I do some other question, Galo? I don't know.
I think we are up to the limit of time.
Okay.
So sorry. Maybe you can deliver a part.
I'll be happy to meet all of you soon, and yeah, we can just.
Yeah, it will be very interesting. Congratulations, Mario. Thank you very much.
Thanks for your question, Daniel. Good to see you.
Yeah. Okay.
Okay, thank you, Daniel. We have time for one question. I saw that Professor Luis Pineda from Yachay Tech asked for. We kindly invite him.
Yes. Thanks, Galo, and hi everyone. Thanks for the invitation. So the organizers to be part of this thesis proposal presentation. Very nice work, Mario. So here in Ecuador, we don't know that much about the atmosphere, so the work you are doing is gonna contribute a lot. So that's great to see that. I have just two questions, but actually I can compact in one because we are running out of time. As I understood, you will be looking to events in the second paper, right? So you're looking to kind of events or kind of weather events. And my question is, I wonder if you are doing or your idea is at the end, of course, there will be an input for the self-organization map work. But as a side product there, you're planning to do a kind of a storm catalog there that it will be useful for us to understand a little bit what is the type or the category of storms that we do have. Yeah. So that's my first question. And the second that I will do right now is about the title of your dissertation. You say precipitation model, but it seems from what I understood that you will be training your machine learning tools on reanalysis. That is a climate reconstruction. All right, and so I wonder if you're talking about prediction. So why you don't use a hindcast of operational models? Some of them are free available, like the ECNW models. They are available for the seasonal and the subseasonal scale. So it would mean if you are talking about probably a model for precipitation, you probably had to train your machine learning tools on a hindcast of that operational models. Okay, that's all.
Yeah. So thank you, Luis, for your questions, and thank you for attending the presentation. Yeah, about the first one, yeah, that's really the idea. That's why actually I separated the first two papers in two working packages, because I think the first two products are also interesting, even though they don't pose a great scientific challenge themselves. So the first one is going to be, well, I already have this regionalization of precipitation in the tropical Andes, which I think is already a useful product. And then in the second one, yes, once the input will be the rainfall events of the radar network. So I will have different storms, and the weather typing by means of the self-organizing maps is going to give us, yeah, as you said, like a catalog of the different kind of storms we can have in the region where the measurements with the radars are being taken. So yeah, you could say that we're going to have a catalog of different storms for the region. And then in the end, we will have also the knowledge about what is the climate the state of the climate that produces each one of those storm types. And yeah, for the second question, I'm not sure if I understood correctly, but maybe the answer is that I'm going to be using historical data already, so I can use the reanalysis data for the 2 papers, because I think that's more reliable than the models that are run by ECMWF, for example. So maybe that could be used in the future, right? When you want to actually implement the model for forecasting in the near future. But for the papers, I'm gonna be identifying the drivers of precipitation and of different storms with historical data. So I think the reanalysis data will be enough for that. I'm not sure if I answered your question.
Yes. Just I was curious about the next step, actually, because it will use this product, this machine learning tool as a post-processing of the operational hindcast. We can do a lot of things when it comes to operational applications, right? So that was my question. But no, very nice and interesting, and looking forward to see your results.
Thank you. Luis.
That's it.
Thanks.
Okay, thank you very much for the public for the presentations, Professor Pineda and Daniel. Thank you so much. It's been a nice presentation and a fruitful discussion this morning, of course. Now it is time to finish this open session for the public, because the jury and the committee will proceed with their private deliberation. Thanks everyone for your attendance to this nice event. We invite you to follow up the events from the Department of Water Resources and Environmental Science. And well, we kindly ask the jury members and the committee to join a separate virtual room. Thank you very much. We will remain with Mario here, waiting for some instructions for the committee.
Gracias, Galito. Uf.
De nada, Mario. Ahora sí.
Gracias.
Voy a parar la grabación. Creo que ahí estamos ahí.